Here we have another decomposition problem, except now we have second order kinetics. So we're going to need a different integrated rate law. This is also on the data sheet. It's 1 over AT is equal to 1 over our initial concentration plus KT. So the problem tells us what our K is. It's 2 times 10 to the minus 3 molarity inverse, second inverse. They give us a temperature, and the reason they give us a temperature is just because each temperature gives a different K. Okay. Then they give us an initial concentration of our compound. So that's like our A naught to be 1 molar, easy number. And they tell us we want to wait until it's 0.25 molar. Okay, so we're going to solve for T. So let's just plug those numbers into our equation. So 1 over 0.25 is equal to 1 over 1 plus 2 times 10 to the minus 3 molar inverse, second inverse times T. So this is going to be 5 equal to 2 times 10 to the minus 3 molar inverse, second inverse times T. So then we just divide and get a time equal to 1500 seconds. Okay, so not too bad. I really do think it helps to organize your information. It helps you keep track of what you have and what you don't have. Okay, so now it wants us to compare the 3 plots we see all the time when we're talking about kinetics in Chem 112. So we have a first order, second order, and an Arrhenius plot. So for the first order equation, we'll use the integrated rate law, so natural log of A at some time is equal to the natural log of our original concentration minus KT. So we're always going to think about these equations in a linear form. So Y is equal to B plus MX. So that means our y-intercept, so our axes are going to be time, and then here we'll have the natural log of concentration, and our y-intercept will be equal to the natural log of our original concentration. And then, because we have minus K, our slope is going to be negative. So slope is equal to negative K. Okay, so moving on to second order, we'll need the second order integrated rate law. So again, we want to think about this in terms of a linear form. So we have y equals b plus mx. Our axes again are going to be time, but now instead we'll have 1 over concentration. So our intercept, represented by B, is going to be 1 over our initial concentration. And because we have positive K, our slope will be positive. And I just want to remind you guys that K is always positive. It's just the slope shows up as going down in first order. Okay, last but definitely not least, we have the Arrhenius plot, which uses the linear form of the Arrhenius equation. So this equation relates rate, represented as K, to temperature and activation energy. So on our axes we'll have 1 over temperature for our x-axis, and then we'll have the natural log of K for the y. So our intercept is going to be the natural log of A, but this is a different A than the ones we were just talking about. Before, we were just using that to be a pretend molecule, but now this A is the Arrhenius factor, and that tells us something about the probability of two molecules colliding and having successful orientation, or successful orientation energy to have a reaction. Okay, and so that's going to be our intercept. And then because we have negative EA over R, we're going to have a negative slope. And that slope is going to tell us about the activation energy. And just a reminder that higher activation energy, slower reaction. Okay, so these are three similar looking plots that you can expect to see on an exam. And just keep in mind that you always want to look at the axes to understand what's going on and to pick which equation describes your scenario. Okay. So now we're going to use the Arrhenius plot. So give us something like what I just drew. Tell us what the slope and the intercept are, and ask us what the activation energy of the reaction is. So we'll need to use the slope, and as you saw before, the slope, which is equal to negative 5413 Kelvin, is equal to negative activation energy over R. Okay. So then we can just go ahead and say negative 5413 Kelvin is equal to negative EA over 8.314 joules per mole Kelvin. And then we can multiply the 8.314 over, and we get that our activation energy is 45000 joules per mole. And if you prefer, you can call that 45 kilojoules per mole. Okay, so not too bad if you keep track of what the slope and intercept mean. So then it asks us how many times faster the reaction will proceed at 350 Kelvin than 300 Kelvin. And so I've written up here in the corner a form of the Arrhenius equation that lets us see the impact on rate as we change temperature. And so when it says how many times faster will this go, they're really looking for is the ratio of K hot over K cold. Okay, so we'll solve for this part inside of the natural log. And we figured out what activation energy is. R is a constant, and they give us temperatures, so we can just go ahead and plug in. So we'll have the natural log of K hot over K cold equal, and I'm going to leave it in joules. You can do kilojoules or joules, it's totally up to you. As long as you match your units to R. Okay. And we'll have 1 over first the cold, and it needs to be in Kelvin, and then the hot. Okay, so now we just have some multiplication division to do on the right. And we get that the natural log of K hot over K cold is equal to 2.58. So again, we get rid of our natural log with an exponential, E. And so that will tell us K hot over K cold is equal to about 13.2. So we can say that at the higher temperature, the reaction goes 13.2 times faster. Okay, now we have a mechanism, and they want us to use these 2 steps, which we can treat as elementary, to figure out the overall rate law for the reaction. And so tell us our first step is fast, second step is slow, and so this will be our rate determining step. And since that's the step that determines our rate, may as well start by writing the rate law from that step's perspective. So we'll have K times NO times NOBR2. Okay, so the problem with that rate law is that NOBR2 is an intermediate. It gets made and then used up again. Okay, so this isn't actually something that we're scooping into our reaction. So we don't want to write the rate in terms of that. So we need to come up with some way to replace it. And we're going to use step 1 to do that. Step 1 is stuck waiting behind step 2, and so it's kind of pacing back and forth. And so we say it's at equilibrium, and so it paces forward sometimes, but it also paces back. So the rate forward is equal to the rate in reverse. So we can write a rate law for the forward reaction. We'll have some K, NO, PR2, And then we'll say that's equal to some other K times the concentration of NOBr2. And so now we have some kind of link where we can get rid of our intermediate. So what we're going to do is move our K over so we can isolate NOBr2, divide that over, and we'll make some new fancy K. And then we can replace, and take this whole section and replace NOBr2. And so then, now we'll have rate is equal to some even newer K, because we keep changing our K with every step. K times NO times NO times Br2, which is equal to K, and we call this usually K observed, because it's what we see IRL, NO squared Br2. Okay. Oops. So then this would be our rate law. So we have some nice third order reaction going on. So now they want us to draw a reaction profile. And so they tell us it's exothermic, which we can take to mean exergonic, and say that we start at some energy level, and then energy exits, and we're at a lower energy. So for each step, we're going to have a hump to overcome, when that's our activation energy. And the slow step's going to have the bigger barrier. So it'll have the bigger hump, bigger activation energy. So we can have something like this. Something like this. It's a little better. Okay. So here we'd have our reactants, our products, so at the peak of each, we have our transition states, also sometimes referred to as activated complexes. So we have two of those, one at each peak. And these aren't real molecules, they're just some weird state where the molecules are twisting into their new position. And then in this valley, we'll have our intermediate then, and that's going to be our NOBr2. Okay, and then we have our two activation energies, and it's much larger for our second step, which is the slow step. And because we went from a higher energy level to a lower energy level, we have a negative delta E. Which is because it's an exergonic reaction. Okay, the final part is looking at chlorofluorocarbons, CFCs, and You guys might be too young to remember when the ozone layer had a giant hole above it, especially near Australia. It's still not totally fixed, but it's a lot better because we stopped using these CFCs. Okay, so let's look at and figure out what the role of each component is. So we can start with the chlorine radical, and we find it here and here. So when something goes into a reaction and then is regenerated, it's going to be a catalyst. So you can see with the chlorine radical, it gets together with the ozone, changes everything up, turns it into oxygen, and then is regenerated. So it can go and find another ozone molecule and do the same thing. And now we can look at ozone. So we only see ozone on the reactant side. So that one's pretty clear, it's just a reactant. And then the oxygen we only see on the product side. So that's just going to be a product. Okay. And then this ClO, we find it first on the product side and then on the reactant side. So it gets produced and then used up. And so that's going to be an intermediate. So it can be somewhat easy to confuse the catalyst and the intermediate, so be careful. But catalysts get used and recreated, whereas intermediates get created and then used up. Okay, so with reference to CFCs, they're dangerous because they do go up to the ozone layer and destroy it and turn it into oxygen. And then there's less of a barrier between us and the UV rays from the sun. And so there was a big global initiative to reduce CFC usage. And they changed that actually very quickly. And so maybe soon we'll be able to have some initiative when everyone gets on board to help fight climate change. Okay, that's all I have to say, so good luck. I hope you zoom through kinetics and have a good understanding of it. Okay, bye.